Today's topic, we return to abstraction. Remember that all the way back from week 1? Abstraction is going to be the way that we're going to be able to create lots and lots of circuits once we have a basic understanding of one. We're just reproducing them like crazy. So here we go. This should be a familiar circuit. It was the first one you built in Logisim. We took an XOR and we stuck a NOT gate on the other side of it. Think about what the algebra for that would look like. Yep, there it is. Now think about what the truth table would look like. And there it is. Now, if you think about this circuit in words, what it's really doing is checking to see if A and B are the same. It's comparing them. If they are the same, the result is true. If they aren't the same, the result is false. So we might call this circuit a comparator. I'm going to draw a box around it, and now with that box around it, we're going to stamp out another copy. Instead of having one comparator, I now have two. So I can put two sets of 2 input into it, and each one will do exactly the same thing. If you think of A0 and A1 as being the first and second bits of a 2-bit number, and B0 and B1 being the first 2 bits of another 2-bit number, you'll see that what I'm doing is comparing to see if those two numbers are equal. Is the 0th order bit the same, the 1's place? And is the 1st order bit, the 2's place, the same? And if they both are the same, then the result is true. So here's a combined truth table for my two sets of comparators. And you can see the combined Boolean logic below as well. Now, this is a little bit weird. It doesn't really get across the idea that we're comparing two 2-bit numbers, either in the truth table or in the diagram. So I'm going to switch the positions of the input. Now I've got the 2-bit number A0, A1 together, and the 2-bit number B0, B1 together. And you'll notice that they're together over in the truth table as well. And now it's very easy to see that whenever A1, A0 is equal to B1, B0, I get exactly the right output, 1. And in all other cases, I get a 0. Now if I abstract that a little bit higher, I no longer care how I implemented the comparator. It could be done any way. It could be done by somebody else. I could buy them off the shelf. As long as I know exactly what it's going to do, I can plug them together and make a new circuit out of them. Logisim supports that, and there's a separate podcast that shows you how you draw a box around something in Logisim and then reuse parts that you've built together. If I wanted to make a 4-bit word comparator here, well, I could stick 4 of these together. I need to handle an entire byte, 8 bits worth on each, 8 comparators. Or, here's a thought for you. What if I made a 2-bit comparator and then stamped out copies of that? Gee, if I put two 2-bit comparators together, I could get a 4-bit comparator and stamp out copies of those. 4 plus 4 is 8. I can stamp out 8-bit comparators. I can stamp out 16-bit comparators. I can stamp out 32-bit comparators.